All right, let's dive into something truly fascinating. We're going to explore how a brand new bridge is being built between two massive worlds in computer science, worlds that for decades have been almost completely separate. We've got the pure abstract theory of simplicity on one side and the practical data crunching power of machine learning on the other. The goal? To teach our machines one of the most powerful ideas ever conceived. So let's start with a huge question. What if an AI didn't just spot patterns in data, but was actually hardwired to find the most elegant, the most compact, the simplest possible explanation for everything it sees? You know, Occam's razor, the simplest explanation is usually the best one. Well, the research we're digging into today is all about embedding that exact principle right into the DNA of machine learning. Now, to really get what a big deal this is, we first have to meet the two main characters in this story. For years and years, they've been running on parallel tracks. Both are chasing the same ultimate goal, intelligence, but they've been coming at it from completely opposite directions. On one side of this massive gap, you have Algorithmic Information Theory, or AIT. This is the deep theoretical world. Think of it as the ultimate theory of what simple even means, using ideas like Kolmogorov complexity. Then, on the other side, you have the hands-on, practical world of machine learning, which uses these geometric tools called kernels to find similarities in data and make predictions. For the longest time, these were like two separate continents with almost no travel between them. But that's all about to change. So how in the world do you even start building a bridge between pure abstract math and practical real-world code? Well, the architects of this bridge started with the most fundamental idea from AIT. The notion that you can measure simplicity by how much you can compress something. And that brings us to this really profound concept called Kolmogorov complexity. Think of it like this. The string 1010101010 is simple, right? Because you can describe it with a tiny program like print 10 5 times. But a random-looking string like 1101001011 is complex because pretty much the shortest program you can write to make it is just print 1101001011. The less code you need, the simpler the thing is. That's the whole game. Taking that idea, researchers created the first pillars for our bridge, these tools called KC kernels. They basically turned these theoretical ideas like compression distance into practical ways to measure similarity. And the intuition is actually pretty simple. If you can compress two things together and get a really small file, they must share a lot of information, which means they must be pretty similar. Makes sense, right? But there was a problem, a big one. These early designs hit a major engineering snag. You can think of it like a compatibility issue. These new KC kernels just didn't have the right mathematical shape. They weren't what's called positive semi-definite. And what that meant was you couldn't just plug them into the powerful engines of standard machine learning models. The whole project was basically stuck. The bridge was blocked. Okay, so the bridge is blocked by this weird mathematical incompatibility. What now? Well, the researchers needed a really clever engineering fix, and they found one in a process you could call mercerization. This brilliant solution is called D2KE, and you can just think of it as a universal adapter. It takes those meaningful but mathematically wrong-shaped measurements from the KC kernels, and it transforms them into valid, usable kernels that machine learning algorithms can actually understand and work with. This was the absolute key that got the construction back on track. With the foundation now solid and those compatibility problems solved, the researchers could finally roll out their master blueprint. And this wasn't just about fixing one little problem. It was about creating a single, universal framework that could bring all these different pieces together in a really elegant way. And this is it, the Solomonoff pipeline. Let's just walk through it because it's kind of like a conceptual assembly line. It all starts with that core idea from AIT. Simple things with short programs, get the most weight. That feeds into step 2, creating a master template called the SFM. From there, step 3 uses a special tool to analyze the geometry of that template. And it all leads to the final product in step 4, a real, working, probabilistic learning model called the SGP. It's an incredible journey all the way from pure theory to a practical tool. Now, the real heart of that whole pipeline is the Solomonoff feature mixture, or SFM. This is the master blueprint for the entire bridge. It's the single powerful mathematical framework that ties together all those different algorithmically inspired kernels. And every single one of them is guided by that core principle of Occam's razor. And if the SFM is the blueprint, then the SKCO is kind of like the structural engineer's toolkit. It's what lets us analyze the properties of the bridge we've just designed. It tells us about the model's ability to learn and, maybe most importantly, make sure the whole thing is mathematically sound and isn't going to fall down. So, the bridge is designed, it's engineered, it's stable. Now we get to the really exciting part, the payoff. What kind of amazing new traffic can this bridge handle? Well, it turns out it enables a completely new kind of vehicle for machine learning. And that vehicle is the Solomonoff-Gaussian process, or SSGP. This is the superhighway of learning that runs across our brand new bridge. It's a powerful, practical machine learning model that has a universal simplicity bias baked right into its DNA. It doesn't just look for patterns. It is fundamentally designed to seek out the simplest explanation for the data. This makes it a real computable version of something called Solomonov induction, which many consider to be the holy grail of AIT. Okay, so we've built this incredible, elegant, theoretical bridge that connects deep theory with practical code. But let's ask the real question. So what? Why does this actually matter for the future of AI? Well, there are a few huge takeaways here. First, it forges that solid working connection between abstract theory and real-world machine learning. It also gives AI a universal default setting, Occam's razor, that bias toward simplicity. But maybe the most profound insight of all is this. It shows us that finding the best way to compress your data and finding the best way to learn from your data are actually two sides of the very same coin. This isn't just a neat trick. It's a huge step toward building more general, more principled artificial intelligence. You know, the researchers themselves put it perfectly. They said, compression and learning are two faces of the same principle. That one sentence is really the central idea that this entire intellectual bridge is built on. By giving our AIs a formal, mathematical language to understand simplicity, this work opens up a completely new frontier. And it leaves us with one final, pretty mind-bending question to think about. What happens when our machines finally, truly understand what it means to be simple?